Good morning, everyone. I hope you all can hear me okay. If you can just type something in the chat that you can hear me okay, that'll be wonderful. Perfect. So I can see a lot of people saying yes, so no technical problems from my end. So thank you, everyone, and welcome to today's webinar, episode 2 on innovation in renewable and sustainable cooling. We will just give it a minute or two more for everyone to join in, and we will kick off in a minute. A brief information about the presenters. We have Dr. a.rezk from Aston University, Mr. Zafer from PCM Products Limited, and Dr. Catrarina Marques from London South Bank. I hope we have Zafer with us already, and Kat as well. Just waiting to see if Ahmed is joining or not. Hopefully he should join in a minute. So thank you for your patience.
Who are we waiting for? Zafer?
Hi, Ahmed.
Me? Yeah.
All right.
Yeah.
Good morning, everyone. I think we are all here now. We will let other people join in as they come in. So thank you once again for joining today's webinar. My name is Durga, and I'll be your facilitator today. And I can see that people are saying that they can hear me okay, so that's great. We encourage your questions, so feel free to type them into the Q&A section at any time, and we will address them at the end. And once again, thank you for joining us. Let's get started. First of all, I would like to request Dr. a.rezk to provide a brief introduction on Reef-UKC. Are you able to share your screen, Ahmed? If you want to present something. And just a brief information about Ahmed. He's a principal investigator for Reef-UKC project. He is an academic in mechanical engineering and leads the research in sustainable heating, sustainable cooling, and thermal systems. His research expertise involves enhancing the performance of thermal systems, including the material to system level development. Over to you, Ahmed.
Good morning, everyone. Sorry, the camera. I have a problem with the camera now. Okay. So I have technical issue today. I will speak. I hope you will listen me. There is no problem with that. So my name is Ahmad, and I'm an academic at Aston University, and the BI of this initiative, Reef-UKC. It's a research network, and with main purpose, and the purpose is to support academics to engage with industry and team up actually to do a good research, and this research to support sustainable and net zero cooling systems. We try to integrate cooling systems or new emerging cooling systems actually with renewable energy resources, aiming to enhance the cooling resilience in the UK and also decarbonize the industry. There is a lot of things we can do here. We can work with the systems itself, and we can work with the energy storage in terms of electricity, in terms of thermal energy, and integrated with renewable resources like geothermal, wind, solar, these sort of renewable resources directly. All the activities here are funded by EPSRC. You just need to participate, and if you participate in person in one of our workshops, all the expenses will be covered. Webinar is free of charge anyway. Also, we announce seed funding calls. So we had one already. We have people working on projects, and the other one will be released in few weeks actually, the round 2. So if you are interested, just keep an eye on our website. All the updates will be announced, and we have your registration information. We will send you email once it's out actually. So I don't want actually to take long time and leave it for the more important people, Zafer and Kat, who kindly accepted actually to present and share some knowledge with the community today.
Thank you, Ahmed. I would now like to invite Zafer, who is the founding and managing director for PCM Products Limited. Zafer, would you be able to share your screen and see if there is no problem? While he's uploading his screen, Mr. Zafer specializes in phase change material-based thermal energy storage and low energy cooling and heating technologies. He's a passionate advocate for alternative energy efficient and environmental friendly technologies. His work focuses on load shifting and site demand management for practical HVAC and refrigeration applications. I can see your screen, Zafer, so
Yep.
you can kick off now. Thank you.
Okay, good morning, everyone. I'm trying to recover the renewable and the sustainable cooling. And of course, we have at the moment current technologies, and the two technologies we can consider either the heat-driven or the electric-driven systems. And I will first of all start with the heat, so we can collect the solar energy in terms of thermal energy. And there are three grades of the application or the levels available. One is a low grade, which most likely the solar collectors, average solar collectors. Low, medium grade, which up to, as you can see, the less than 100 degree, and the high grade. And with solar thermal, which we have seen these big towers and mirrors and everything. There are a number of technologies which I won't read them, but there are ejectors all the way to the vapor compression, thermoelectrics, and absorption, adsorption, any other cycles. But generally, those machines taking heat and converting into cold energy, and energy in the region of what we are aiming, three scales. One of the air conditioning HVAC side between 5 to 89 degree range, chilled. Of course, we are aiming the chilled food 2 to 8 degrees C as well as the frozen. And the most common, widely used technology, the heat-driven machine, is the absorption or adsorption type machines. And these machines basically take the heat and using an absorber and circulate the refrigerant. And the lithium bromide is the most common workhorse of heat-driven. And within the lithium bromide absorption machine, the working absorbent is lithium bromide salts, but the working media, the refrigerant, is water. Hence, it limits its ability to produce cold water no lower than 7 degrees C. That's the limit for the water absorption machines, and therefore lends itself on a just simple air conditioning or chilled or cooling application down to the basically maybe 7 degrees C chilled water. There's an application typical, for example, one in Qatar, this FIFA World Demo Stadiums. As you can see, collecting all the solar energy, putting into the hot oil. Hot oil drives the absorption machine, produce cold water. The second type of absorption machines are the ammonia. And the beauty of that, the water is the absorbent and the refrigerant is the ammonia. And if you have ammonia as a refrigeration, you can go as low as -40. So therefore, it lends itself very nicely onto the refrigeration cycle. The simplest form of ammonia absorption machines, maybe you came across these silent refrigerators in the hotel rooms. And they are the basically heat-driven absorption machine and with using ammonia as the refrigerant. The next stage will be this medium scale commercial application of ammonia absorption machines, but generally aiming for the commercial air conditioning sector rather than refrigeration. And you can go basically one stage bigger, these big monsters on industrial scales applications, and it's been widely applied, but of course it requires a significant investment. Really, those are the thermally driven technologies already out there, but all you need to do, justify economically and technically make it viable. Where do we apply this cold logistics? There are 4 common applications. The first one, 2 to 8 degrees Celsius, which generally named as chilled. Ambient, which is becoming critical because getting warmer and warmer. Certain products, food products, medicines, and especially like the chocolates, has to be kept within a reasonable temperature, ambient temperature. Frozen, it could be anywhere between -3 to -34 as a general frozen food applications. And the next one is basically the ultra low temperature, generally on the pharmaceutical, medical sectors, biological samples. I think on the food sector, the only application, as far as I'm aware, is the tuna. Tuna has to be frozen is -70. Really, where basically this chilled or frozen or ambient from production, the raw materials getting into the factory throughout the production, storage, logistic, delivery, and consumption, we need to control the temperature. If it's a temperature control logistic, it has to be maintained whatever the acceptable limits. And also, of course, the food products are far more susceptible to the temperature, especially if we are aiming from farm to fork concept of cooling, mainly the cooling applications of these food products. The most important one is on the left-hand side, harvesting. The faster you cool the product, the longer the shelf life. And that is a example, like especially places like Africa, India, half of the food products is being spoiled and lost because the lack of cooling. But as you can see, if you have solar-driven independent refrigeration modules next to the harvest, you can collect and cool straight away. They are off-grid application. Here is one example of that. And of course, you can bring it back to the main static solar-driven cold stores, and therefore you can provide throughout this chain as a solar renewable energy driven refrigeration logistic. And of course, the cold stores and the consumption, even the consumption using ice packs to deliver. So therefore, really the possibility of looking of what energy available, what we can use, and how do we diversify. The biggest problem with the renewables, whether it's wind or solar is basically only maybe 8-10 hours at best is available. The rest of the night, what do you do with it? Or wind is unpredictable, comes and goes. So therefore, the renewable basically cycles unpredictable fashion. But nevertheless, on the right-hand side, the energy use, the demand is 24 hours, constant. So there's a gap between the available energy and energy use. We need to bridge that gap. At the moment, there are 2 technologies we are using bridging that gap. One is thermal storage. We can store the energy when it's available, renewable, put into the thermal form, hot, cold, but also we can use batteries to charge and run mechanical refrigeration. Either way, and we need to find the balance between the thermal storage battery economically, environmentally. One of the obstacle with the batteries, there's a lot of environmental concerns. All the materials being used. Life is another issue. Every maybe 5 years you need to replace. And of course that add up the life cycle cost. And the weight. Weight is another issue, big issue, which I'll cover a little bit later. And really, why do we need thermal storage? Without the thermal storage, the renewables will not work. Or battery storage, some sort of storage is essential. One of the advantage thermal storage is far, far cheaper in investment cost and far, far simple and environmentally friendly because products on the chill and the frozen side, water and the salt mixtures, they are all natural. They can go back to the earth where they came from. But also thermal storage offers the various advantages. First of all, we use, especially if we are capable of within the design, run the machine overnight. 10 to 15 degrees C lower nighttime running machine, you will be physically saving 20-30% of your kilowatt hours electricity consumption on a mechanical refrigeration. That's a big saving. Secondly, of course, we have varying half an hour electricity rates and tends to be early hours in the morning, electricity is the cheapest. Or if you have solar and wind available, renewable, you can capture that when it's available. And of course, this solar and wind is the driving factor for this to be able to store that energy rather than paying wind turbines not to run. And of course, thermal storage, like the battery storage, will give you the standby capability. If there is a mechanical failure or power failure, it will keep it going, the process, and protect the product. How do we do it on the refrigeration bigger field? And the simplest form on the left-hand side, all we go to picnic, we freeze these blue bottles on the left-hand side, top side here, and overnight and put into the cold box, keep the product all day chilled and cool. And that basically the same concept can be applied at cold room. And we can put the basically ice cubes. The difference is we manually handle the ice cubes. In the cold store, we cannot do that. We have to do in situ, somehow freezing and melting, and therefore shifting the loads. Here are the typical examples on a cold storage applications. You can see that these ice cubes, if you like, could be either within the racking on top of the products, or you can put pallets within the like a standard pallets and create artificial loads. It could be on a small scale installed on the ceiling. And whatever happens, we are putting these ice cubes into the cold room. And when the surplus energy is available from the machinery, we freeze them. And when the heat and the load comes back, and they hold back the refrigeration and absorb like a sponge, soaking up the heat in the cold room. So therefore, we are in charge of when to run the refrigeration, when not to run. And that's crucial on a renewable, because we want to capture as much as renewable energy as possible. Another thing's basically what we are facing. If it's a static application, it doesn't matter how heavy the batteries, PCMs and everything, you can handle it. But when it comes, the whole purpose of basically this electrification of transport, going the EV, electric vehicle transport refrigeration, it becomes a major issue. Whether is you balance the battery or the thermal storage to find, because the limits, as you can see on the right-hand side, 3.5, 7.5, 18, and maximum 26 tons on the delivery lorries. Now, as soon as you remove the engine-driven mechanical refrigeration and try to drive that refrigeration with the batteries, now we have a problem. You need awful lot of batteries to run the refrigeration. And as a result, you restrict it with the weight of the vehicle altogether, including goods. Either you end up carrying only the batteries, no goods at all, with a cold, empty chamber, or you compromise significantly in terms of the range, and because also same battery driving the vehicle. So therefore, that is at the moment the challenge, finding the way, how do we find a solution, these EV revolutions of, especially on the refrigeration. When we move the engine, now we have a problem. That really becomes a critical, as a basic study you can see here, in comparison with the thermal storage versus the battery storage for an average 20-foot container size and a 40-foot container size. They just only the basic study here. But looking through those graphs, if you look at the dark blue ones, frozen applications, certainly electric batteries are not an option. It's almost 3 times more weight in terms of the operation. So therefore, the thermal storage for a frozen application looks very, very attractive if you look at these comparisons. Chilled is almost equal, or sometimes on the 40-foot container, 30-40%, and it could be balanced or hybrid, battery plus chilled applications. But on the ambient shipments, the battery really overrides the thermal storage. Thermal storage becomes far too heavy to justify, and therefore the ambient could be the battery-driven refrigeration. Chilled, it could be hybrid or PCM or the thermal storage, still unattractive, but on the frozen, certainly it's the way to forward will be the eutectic type thermal storage applications for the EV transportation. Here are the typical example what you can do with the solar and electric driven variations. These basically the products has been applied in Africa for the harvest. As you can see in the field, as soon as it's collected, you can cool. But whatever we do, whatever we basically apply, we must have some sort of storage, whether it's the battery in this case, or thermal storage, as you can see on the ceilings here. So therefore, thermal storage will be essential, vital part of the basically renewable refrigeration technologies in the future. Here is Of course, on here, as I mentioned, the weight is critical. So you need to find the balance between the thermal and the battery weight, because road restrictions limits what you can do on top of the refrigeration units. But if it's static, it doesn't matter. You have the facility to do, and it's widely used, very common standard product, solar refrigeration, cold stores available. They work well, but whatever you do, either you store the batteries, some sort of energy to handle the nighttime cooling process, or as you can see here, a simple eutectic static maintenance-free products. Use the sun when it's available, freeze them, and nighttime it become like a cold box. And this frozen energy soak up all the heat until the sun come back. Conclusion, heat-driven system generally tends to be the large installation, industrial process type installation, because of the cost, because of the complications. And the PV-driven systems, the photovoltaic electric tends to be stick on the smaller or the medium size applications. Thermal storage, as I mentioned, the reason I explained before, it's vital part of any renewable refrigeration systems to be able to store. It is far more cost effective than the batteries, and environmentally is probably far more attractive because of the simplicity. And one has to find the balance between the battery and the thermal storage, not only the weight-wise, but also cost-wise life cycle. And therefore, it needs to be carried out some sort of studies to evaluate which one is better. And another things what we need to look at is especially the EV transport type refrigeration, improve the insulation quality. So better the insulation, lower the loads. That means lower the weight and the cost of the system to drive the refrigeration. And finally, if anybody basically needs as further information or the publication, I put two of those very useful reference data there. One is the Institute of Refrigeration conference papers. There are a lot of papers covering theoretical, practical examples of this renewable refrigeration on that conference, ICC 2020. Another useful basically the reference is International Institute of Refrigeration in France published it's free to download, is a very good long detailed guide on renewable refrigeration application globally. So it's a very useful two references. You can go and get more information, but equally if you have any other questions, either you can drop on the chat line or drop me an email if you wish to receive the presentation as well as any questions you might have. Thank you.
Thank you, Zafer, for this amazing presentation. As I mentioned, please feel free to drop your questions in the Q&A section, and we will address at the end. I would now like to invite Dr. Catrarina Marques, preferred name is Kat. She's a senior research fellow at London South Bank University. Dr. Marques has over 18 years of experience in funded research projects across food, science, refrigeration, and district heating and cooling. Her PhD work on domestic refrigerators earned prestigious Ted Perry Award from the Institute of Refrigeration in 2012. She has successfully bridged the gap between academia and industry through an industrial case and award PhD to knowledge transfer partnerships with Adende Refrigeration, where she has also led the engineering department and contributed to the award-winning product development. Over to you, Kat.
No, thank you very much for the introduction, Durga. I'm just trying to upload the right presentation, so just bear with me for a second.
No worries.
It's uploading. But yeah, it's a pleasure to be here, and thank you for the invitation. And let me know when you can see my slides. And it's also great to see so many people here.
Brilliant. Yeah, thanks, Kat. We can see it now.
Brilliant. Thank you.
Thank you.
So today I'm going to be presenting about cooling in the UK, and I'll be presenting the findings from our TICA project, and TICA stands for Transport, Industrial and Commercial Refrigeration. So this is a project that's been funded by the UK government and is a collaboration between industry and academia. But let me set a bit of the context behind this project. So the starting point, well, there's an industrial decarbonization strategy published by government in 2021. The aim is to get industry to achieve net zero by 2050. And this is through the adoption of clean technologies, energy efficiency measures, and collaboration between industry and government. Now, in reality, energy and emissions from cooling in the UK, they are still emerging data. So this has led to two projects, the CS Now project and the TICA project. So CS Now investigated the emissions from comfort cooling, from domestic refrigeration, and from mobile air conditioning. And then the TICA project looked at all the other sectors. But you know, at global level, there's been a lot more focus on cooling. So the Global Cooling Pledge was signed at COP28. And the pledge sets the commitment to work together to reduce cooling-related emissions across all sectors by at least 68% globally. And this is, yes.
Sorry to interrupt you. I can't see your presentation. I'm not sure if others have the same issue.
Oh, thanks for flagging that. It seems fine
No
on my
worries.
side, but I will. Oh, thank you
It's
all.
the same at the other's end as well.
Okay, so just bear with me and I will try something else.
Thank you.
No, thanks for flagging that.
That's right.
Okay. Yeah, still loading. While it still loads, I might just, carry on telling you a bit more about, the Global Cooling
If you
Pledge.
want, I can present from my end.
It's just, I think if you just give me a few
Sure.
seconds, I think it'll be okay.
I think it's fine. It's fine fine. I mean, I can see people are saying it's fine now, but from my end, I can't see it. But I think you can continue.
Okay, it might be a delay from my end then, a poor connection. Apologies for that.
No worries. Yeah, we can carry on.
Let me just. Okay, I think some people could see it, some others couldn't. But I'll share my slides again. Okay.
Yep, there you go.
It's working. Excellent. Yep. Fantastic. So I was just telling a bit about the cooling pledge. So this sets the commitment to reduce emissions at worldwide level. And so far, there's about 71 countries that have endorsed the pledge. Now, the UK government was highly involved in drafting this document. And the next step for the UK is to develop a UK cooling strategy. So government plan is to publish a cooling outlook next year. And the TICA project is feeding into this work. But looking at the TICA project in more detail, so we looked at all these sectors. So we looked at transport, road transport refrigeration. Within industrial sectors, we looked at chemical and pharmaceuticals, food and drink, data centers, cold stores. And within the commercial sector, we looked at retail. So this is supermarkets, but also convenience stores. So the project aim was to develop a data-driven approach to support decarbonization and innovation across all these sectors. So we started by estimating the emissions from refrigeration and from cooling. We carried out over 50 site surveys, and this was to identify what's current industry practice. And when data was available, we developed benchmarks. We are producing end user guidance. and roadmaps. So we looked at all the technologies within these sectors and how they can achieve net zero. And finally, we looked at what are the policy opportunities to really accelerate this transition to net zero. So let's have a look at the UK cooling emissions. So this chart shows the emissions for residential and non-residential buildings and transport. So the blue bar shows the electricity use, so scope 2 emissions, and the green bars are scope 1. So light green is from refrigerant leakage and dark green is from fuel usage. So you can see that the non-residential buildings overall have higher emissions. I've highlighted in these boxes the sectors that were covered in the TICA project. But overall, cooling accounts for 4% of the UK greenhouse gas emissions. So it might seem like is a relatively low percentage of the emissions, but cooling emissions are set to increase because of rising temperatures, population growth, economic growth. All of these are factors that are likely to increase emissions. So we really need to focus on improving the efficiency of the system so that this doesn't happen. And this chart shows the energy that goes into cooling. So you can see that domestic refrigeration is the highest energy user. So it's about 1/3 of all the energy. But data center cooling is actually increasing, mostly because this sector is increasing drastically due to artificial intelligence. So there's many data centers that are at planning permission stage. So they have high requirements for cooling. So overall, cooling uses 15% of the UK electricity consumption. So it's quite critical to, again, look at how we can reduce energy use in cooling. But just a bit about what's happening in practice with in the industry. So we did 50 site surveys. It was 10 for each sector. So supermarkets, cold stores, data centers, food and drink, and chemical and pharmaceuticals. And actually, what the findings were actually quite common across all sectors. So overall, we found a lot of poor design and maintenance and a lack of focus on energy efficiency. So the focus is on keeping the system running rather than improving its efficiency. But so the best practice really would be to submeter the energy use for the refrigeration systems and for its components. And in some cases, we did see a bit of proactive refrigeration optimization, so against the digital twin. But this is still very uncommon. What we also find was a lot of high condensing temperatures. And this is a picture of a blocked condenser. And we found these, all the way from supermarkets to data centers. So there's a lot that can be done with improved maintenance. So there's opportunities to install variable speed fans and motors that adjust the speed to the load. In terms of improving efficiency at the design stage, one of the most important things to do is to increase the evaporating temperature. But this needs to be done at the design stage. We also found that F-gas logs were not always available on site. So that's a kind of a legal requirement to have the F-gas logs. They might exist, but they were not available on site. And it's critical to implement a preventive maintenance plan. So, the key is that needs to be a bit of better communication between end users, the refrigeration contractors, the technicians, and the designers to make sure the system is not just running, but is continuously improved. We also developed a benchmarking tool. So this is a survey that end users can complete to compare how they are operating against our set of recommendations, which come from findings from site surveys and from research. And this is an example of the kind of questions that are in the survey. So at the end of the survey, the end user gets a ranking, well, the silver, bronze, or gold, which depends on how they responded to the question. So it gives them an initial assessment of areas that they can improve. But when data is available, then it's possible to do something more. And this is an example for cold stores. So for cold stores, there is data that's available through the climate change agreements. And basically, this chart shows the specific energy consumption for different storage volumes. So we've put some curves through the data. So you can see the high energy users in the red line, and you can see the green line, which is really best practice. And the blue dots that are shown in the chart are actually the sites that we surveyed. So you can see they are actually quite representative of the market. Now, for other sectors, it's a bit more difficult to produce these benchmarks because the data is not always available. But if we look a bit into what are the technologies available, we reviewed an extensive list of technologies. This is just the top 10 technologies for retail and is actually focusing on major retrofit. So we looked at, for the different technologies, what would be the scope 1 emission saving, what would be the overall system energy saving, the payback period, and again, whether it would be easy to retrofit on an existing system or would require a major retrofit, so essentially a new system. But we looked at all these technologies and we looked at what is their impact on the overall system energy use. For instance, if we had a technology that had a 50% energy saving over conventional technology, let's say a defrost, for instance, but defrost is only responsible for 3% of the overall energy use. So we did this balancing to see what was the contribution of the technology to the overall system energy use. And for retail, I mean, the biggest intervention is actually replacing the cabinets with the best available on the market. So right now, believe the best is a cabinet that's rated a B. But there is other technologies. So short air curtains is an example, ejectors, boreholes, looking at different, using low GWP refrigerants. There's all these options. And, the cabinets that are the best ones available on the market, they all have doors. So that definitely reduces infiltration and reduces energy. For cold stores, we did a similar assessment, and you can see the right-hand side table shows the share of the overall energy use for chilled and frozen cold stores, and you can see, the contribution from all the components. So in this case, demand side response is the one that actually has the biggest impact. And, demand side response works really well when you combine it with solar PV and also with thermal storage. So the presentation from Zafer earlier fits really well into this. The best thing is always to integrate technologies. So the other option that we looked at was about reducing the set point for frozen cold stores. So there's a bit of more research that needs to go into this area, but the impact that we looked at here is to reduce frozen temperature to -18 to -15. That would be a system energy saving of up to 10%. So there are other options looking at inflatable seals to bridge the gap between the transport vehicles and the loading bay doors, because, in what we found in the site surveys is that normally in many cases there's gaps, so there's entrainment there. But so based on our research, based on the site survey findings, we are producing end user guidance for each sector. And we actually came up with the simple guidance for the end users on things that they can do. And the first one is really to prioritize efficiency and to assign responsibility for refrigeration efficiency so that this is correctly managed. It's important to address the information gap, so to measure and monitor the energy use of the refrigeration system. And just a bit on that, just an example, in cold stores, only 25% of the sites that were surveyed, they had functioning sub-metering. But when that data existed, it was not accessible for the refrigeration technicians that were servicing the equipment. So there is a bit to do on addressing this information gap. It's important to know the assets, understand how they were designed, because sometimes they have a design point, but over time with maintenance, this is no longer being used and the systems are not as efficient because of that. So coming back to what I said earlier, it's important to take a systems approach, so integrate technologies as much as possible. So I'm talking about integrating with renewable power, with thermal storage, with waste heat, integrate heating and cooling. Also think long term about, end of life replacement for the existing equipment, and make well-informed decisions, because especially in the industrial sectors, equipment can be installed now and still be operating in 30 years, 20 years. So it's important that we make the right decisions now. So we are producing a big roadmap. It's going to be published by government, and it covers all the sectors. Is going to summarize the options for policymakers, for end users, summarize all the technologies, and really how to get to net zero. And then we have some technical annexes that go into more detail into the methodology and how we did the research for all of these sectors. And just to show you a bit about how we looked at decarbonizing, in this case, two sectors. So I'm just going to focus on supermarkets and cold stores. So this chart shows you basically the energy used for supermarkets. So we have a dashed line in kind of in the middle of the chart. So on the right-hand side is the potential energy savings beyond the system boundary. So looking at PV and waste heat. And on the left-hand side is the energy consumption that's associated with refrigeration in the store. So the first blue bar shows the baseline, so how much energy goes into refrigeration in supermarkets today. Then we looked at, okay, let's project to 2050 and what are the interventions. So first we look at what's the impact of population growth, because that will increase the number of supermarkets and equipment available. What's going to be the impact of climate change? So how is that going to affect energy use? And then we look at, okay, what if operation and maintenance is improved? And this is when we start seeing the reduction in emissions. But the biggest impact is actually replacing the cabinets, so with the best available on the market. So let's say that if progressively the least efficient cabinets are removed from the market, that would can have an energy saving potential of 65%. So this is quite significant. And beyond the boundary is we looked at the potential to integrate PV on the roof of the supermarkets. So this would be, using 50% of the roof space area. And we look at what's the potential for recovering waste heat. So we did the same thing for cold stores, so a similar chart. In this case, we also looked at, what's the impact of raising set points for frozen storage, and that would be a 10% efficiency gain. So, but there is more research that needs to go into this because one, we only looked at cold stores. It can be applied throughout the whole cold chain. But the research is needed more on what's the impact on the food quality. We know food safety would be maintained at -15 or even higher temperatures, up to -10, but we don't know how it would affect the food quality. And we actually have a PhD that we are advertising at the moment. So we're looking for a student to carry out this research. So we're going to be publishing these documents for end users and for policymakers is the roadmap and the policy options to accelerate decarbonization. So I think we have, this is our project website, so netzerorefrigeration.uk. So this is where we'll be publishing the roadmaps, the end user guides, and the benchmarking tool. So this is all the partners in the project, and I think I'll close there, and thank you.
Thank you, Kat, for amazing presentation. And we have a question from Ahsan, and I think Zafer has already answered that, but I will read it to all attendees. How long is the chemical stability of PCM you're using for cold storage, and how do you compare it with lifetime of chemical batteries? Zafer, you have answered it already, but if you want to come on the screen maybe and give it a brief overview of what. Are you still there?
Yeah, I'm still here. Yeah, I already replied, but I missed the battery bits. I mean, the solutions we are using are water. Basically, what we are doing, putting the various salts to depress the freezing point of water, taking beyond zero, all the way we can take water down to -74, using different salts. Those salts, all they do really depress the freezing point, but the working media is water. So I always ask that question. If you have a bottle of water, how many times you can freeze and melt? Or you take the ice packs you put in the freezer for taking to the picnic for the cold bugs, their life is forever. As long as you don't puncture, if you go above 100 degrees, the water will turn to steam. And if you contaminate, put different salts and everything, the temperature will change. So therefore, as long as it stays within the encapsulated containers, the PCM, especially on the chilled and frozen application, life is not a problem. We have been supplying these for more than 35 years now. The batteries, unfortunately, it doesn't matter what sort of batteries. Generally, people tend to use deep cycle batteries, which are widely available up to 120 amps, or you can get lithium-based batteries. But whatever happens, the battery is the biggest problem. First of all, the cost is far higher in cost. Secondly, to produce batteries, you have awful lot of energy. It goes into the minerals harvesting. And unfortunately, by the average batteries, probably they are talking about 5 years lifespan, or at best, maybe 8-10 years. So therefore, you need to replace those batteries over its lifetime of maybe 30 years, average cold room operation. So therefore, you replace the batteries 3 times, and the eutectic systems and the thermal storage remains the same cost from day one for the next 30 years. So those are really the 2 comparisons. But having said that, you don't have to choose one or the other. You need to find the balance, as I mentioned, the economics life cycle cost what it is because someone is paying the money. But sometimes especially on the transport refrigeration is the weight. Weight becomes an issue because the less goods you carry, it becomes far more expensive per packaging, per kilogram of goods you are transporting. So therefore, you need to find the balance between, it could be a hybrid system, half battery, half thermal, but whatever happens, we need to store energy. Unless we store the energy, renewables are useless because unfortunately, we need to bridge that gap between energy availability and energy use. And thermal storage is another tool in our toolbox. And therefore, it has to be used cleverly, economically, and practically. But certainly, life cycle wise, the thermal storage is far more attractive economically as well as environmentally. I hope that answered the question.
Thank you, Zafer. Next question I have from Syed. How can the supermarket sector realistically achieve the projected 65% reduction in electricity consumption by 2050, and what policy or market mechanism would be most effective in accelerating the adoption of best available refrigeration? Is it for Cat?
I think so.
I guess so. I didn't mention anything supermarket, so
Thanks, Kat.
it's that.
Yes. So our recommendation is that cabinets that are less efficient are progressively removed from the market. So on a labeling of A to G, over time you start by removing G, E, D. So you end up with only cabinets that are rated B. So that would be the policy mechanism that would make this happen. I think is a best approach, a better approach than actually mandate doors on cabinets, because then you have more flexibility for innovation. It's likely that we'll have doors, but if you apply a policy in this form, then you still leave room for innovation. So hopefully that answers your question.
That's great. Thanks, Kat. And the follow-up question, I think there's another one, which is from Hassan. What are the retrofitting challenges in decarbonization of existing assets in cold chain, especially supermarkets, cold stores, and retailers? I think it's again for you, Kat.
Yes, it is. The pity I didn't have any slide on the top 10 technologies for retrofit, but I mean, supermarkets, what we found is they are trying to sweat their assets. In the past, they used to do full refurbishments every 15 years, and now they are trying to actually increase the longevity up to 20 years. But the retrofit, I think they tend to happen more every 7 years. But there is challenges in doing so. I mean, in sectors like data centers, any retrofits are a major problem because they cannot have any downtime, and they actually build a lot of redundancy into their systems. Yeah, specifically for supermarkets, and yeah, supermarkets do it every 7 years. I can perhaps send you a list of the technologies that